The last comment I'll make as an introduction to this discussion of standard quantum mechanics as it currently exists, and the fact that there's three families of theories, is to talk about each of these theories in relationship to the Pauli exclusion principle. For example, the descriptive quantum mechanics, it's a standard fundamental tenet of the theory that both electrons and helium have the same energy. They're both s electrons, they're in the ground state, they must have the same energy. Okay, if we talk about the third family, the Hartree-Fock family, the kind of mixture of descriptive quantum and quantitative quantum mechanics, that hybrid theory, whenever they do the calculations for a two-electron atom, whether it be helium, lithium, missing an electron, whatever, they always are going to insist that both electrons have the same energy. That's going to be a starting point. They're going to make their calculations work so that both electrons and helium are at 24.7. And we've already described how that doesn't make any sense. Because if they're both at 24.7, when you start, one gets ionized and the other one falls to 54.4, that's actually means that the helium ion is more stable than the helium atom, because you actually get 5 electron volts plus from that reaction. Write it down yourself and you'll see that. And as I described before, if you start with that ionized electron at minus 54.4, there's no energy in the process that we observe to bring it back up to 24.6 electron volts. What's really interesting is when we look at the Pauli exclusion principle in relation to the real deal, standard quantitative quantum mechanics, the Schrodinger equation version. It actually makes no sense to talk about the Pauli exclusion principle. It's complete gibberish. It's like talking about the fundamental color of a triangle, or the temperature of black, or something like that. It's just, you're mixing and matching things that don't mix and match. Because as I explained, for example, a 10-electron system, all the electrons are indistinguishable. The Pauli exclusion principle tells you, no, if I have a 10-electron system, I have 2 s electrons, 6 p electrons, and a couple of d electrons. Well, which 2 of the indistinguishable electrons are in the s state? Which 6 are in the p state, and which 2 are in the d state? And there's only one wave function. There are no s orbitals and p orbitals and d orbitals. There's only an orbital, and they're all in it. So this hydrogen model, which is the basis of the Pauli exclusion principle, doesn't make any sense. It's gibberish in this model of quantum mechanics. You can't talk about the 2 electrons in helium are in one state, etc., because the language doesn't fit. There's only one orbital. All the electrons are in it. They're all indistinguishable. You can't say 2 are in this one, and we have 6 others that are indistinguishable in the next hydrogen-like state, etc. So it's just interesting to reflect on that before we go into more detail on each of these families of theory.